The purpose of this video is to introduce you to mineral identification, which I find is one of the most problematic areas for introductory geology students. So here we go. The first thing that we can think about when we're talking about minerals is what exactly is a mineral? So here's the definition. Remember that there are 5 properties that we can talk about that all minerals have. And the first one, the easiest one, is that all minerals are solids. So we're not going to have a mineral that's a liquid. We're not going to have a mineral that's a gas. We're only talking about solids. The next property is that minerals are formed from inorganic processes. What we mean by the word inorganic is that they are not mediated by life. We can have a special type of mineral, which is called a biomineral, that is mediated by life. And so examples of these include the shells that you might find at the beach. Those are made of aragonite. And also the minerals that make up your bones are biominerals. The third requirement of minerals is that they are naturally formed, not by man-made processes. So we can have man-made or synthetic minerals that are formed by humans, but these are not considered to be natural minerals. The fourth requirement of all minerals is that they have a specific chemical formula. So in this example here, we're looking at quartz. Of quartz, we're looking at quartz. This has a specific chemical composition of SiO2, silicon dioxide. Every variety of quartz that you will find always has a chemical composition of SiO2. And then finally, all minerals have a specific crystalline structure. This crystalline structure is very important because it tells us how those atoms stack up and how they bond. And bond strength is very important in terms of fracture versus cleavage. If all bonds are the same strength, then you will break this mineral, but it won't break in a preferential direction. If, on the other hand, you have weak bonds in this crystalline lattice, then those are going to be the ones that break. And that will determine cleavage, which we'll talk about in a couple moments. Before we talk more about minerals, I wanted to revisit the idea of mineraloids, which, remember, are substances like minerals, but they lack a crystalline structure. What you see here are 2 specimens of limonite, which is commonly found as a cement for sedimentary rocks, which means that they sort of glue those pieces of sediment together. So in these 2 samples, we are lacking a crystalline structure. Similarly, in this sample of wood opal, which was recovered from California, we are lacking a crystalline structure. Another special type of mineral, biominerals, include these shells, and remember that one of the requirements for minerals is that they are formed from inorganic processes. Biominerals, on the other hand, are formed with the help of life or through organic processes. Now this is the sample that I was holding at the beginning of the video. This is our friend quartz. And in these specimens of quartz, you can very nicely see those crystal faces. So those crystal faces are the way that that crystal grew, and it didn't run into anything else. It was not restricted when it was growing, so it was able to form these beautiful crystals. But you might notice that we only have the crystals on the top part of this specimen here, and then we sort of have a jumbled mess down here. If you can see nicely developed crystal faces, these crystals are called euhedral. If, on the other hand, you cannot see nicely developed crystals, these crystals are called anhedral. If you have crystals that are growing that are clustered, you will end up with very small crystals that you cannot see the individual crystal faces. So in this specimen of amethyst, we have beautiful euhedral crystals up here. We have, still beautiful in their own way, anhedral crystals down here. And then at the very bottom, we actually have another crystal type called cryptocrystalline. In this sample of chalcedony, this is comprised of cryptocrystalline quartz, which is called chalcedony when it is layered, as you can see here. Now, what cryptocrystalline means is that we can only see those crystals under magnification. So we cannot see those crystals with the naked eye. Now we'll begin covering physical properties of minerals. The first thing that you might think is the easiest is actually the most deceptive. So please never, ever, ever identify a mineral only by color. For example, we have 3 different varieties of quartz in each specimen here. Amethyst is the purple variety, quartz is the clear variety, and then again we have that chalcedony here at the bottom. Quartz isn't the only culprit that does this. Here are 2 samples of plagioclase feldspar. As you can see, they are drastically different colors. One thing that we can talk about when we discuss crystals or minerals in general is their clarity. Now, if something is transparent, that means that you can see through it. And in this sample here, you can see that these crystals up here are indeed transparent. These crystals down here are more translucent, meaning that they transmit a little bit of light, to even opaque, meaning that they transmit no light. Here's a variety of quartz called jasper, and as you can tell, this is opaque. This does not transmit any light. Crystal form is the geometric shape of a mineral. So I keep showing you these samples of quartz because we've got a lot of samples of quartz at Sandjack. But you can see that no matter what the variety, they always have the same sort of shape. So here you see that they have this elongate shape. And the wonderful thing about quartz, and this goes back to the crystalline structure, is that every single crystal might have different sizes of the faces, but the angles between each face will be the same. And again, that is dictated by that crystalline structure, that arrangement of the atoms. Remember that crystal habit is how the crystals grow. So there are several types of crystal habits that we can talk about. The one that you can see here is cubic habit, which is when your crystals have 6 sides. So it might be difficult to see in this sample, but every time that you see a little shimmer in this piece of fool's gold, that is because light is reflecting off of one of those crystal faces. And if we were to look under a magnifying glass, we would see that each of these looks very similar to this, only smaller. We also have octahedral habit, which has 8 sides, which you can see in this photograph of fluorite. Here come the soccer balls. I like to call garnet, which is the January birthstone, little purple soccer balls. These are 12-sided crystals called dodecahedrons. Sometimes you can see very nicely these crystal faces. Other times they're much more obscured. But nevertheless, these are 12-sided crystals. We can also have rhombohedral habit, which you can see up here. These look sort of like a smooshed shoebox, but they're essentially a rectangle that has been smooshed. This is not a 90-degree angle. It's about 60 degrees. So again, this is rhombohedral cleavage. It has 6 sides, and those sides do not align at 90-degree angles. We can have botryoidal forms, which means that it's bulbous or bubbly masses, as you can see in this sample right here. In this photograph, you can see a blade of selenite. This is actually referred to as a needle. And in this photograph, you can see some fibrous gypsum growing in a cave. If you have crystals that are elongate in one direction, we call those crystals elongate. If, on the other hand, we have crystals that are about the same size in all directions, like our garnet here, we call those equant. One of the easiest physical properties to identify is luster. Luster is defined as how a mineral reflects light. For the purposes of this class, we'll only be talking about two different types of luster: metallic, which is what you see here, and non-metallic, which I'll talk about in a moment. All of these samples look like metals, which is why we call them metallic. If you thought this is an example of gold, I have fooled you. This is fool's gold, also known as pyrite. This here is a sample of native copper. This is an example of hematite, and this is an example of magnetite. Anybody want to take a guess as to how it gets its name? One of my favorites is this guy right here. You're probably very familiar with this if you've ever used a pencil, because it's graphite. Now, especially with metallic luster minerals, we have to be careful of tarnish. So you notice here that this copper has this wonderful copper color on this edge, which has been recently broken. But over here, you see that it's got a little bit of green funk on it. And this green funk is called tarnish. Tarnish can occur when the mineral reacts with many things, including air. And so this is why you commonly see copper on buildings or old pennies that has turned a brown or a green color. And that's just because of the chemical change that that surface is undergoing. In terms of non-metallic luster, likely the most common one that you will identify is glassy or vitreous luster. Again, these are less important. The major subdivision is whether it's metallic or non-metallic, but there are several different ways to identify or characterize these non-metallics. So if it's glassy, it will reflect light like a pane of glass, which is what you see the camera is picking up here. Other types of non-metallic luster include waxy, where some people might say it looks like candle wax. People might also call something pearly. This sample of gypsum sometimes has an iridescent sheen to it. You can also characterize dull or earthy. These are things that look like perhaps the soil. They don't really reflect light very nicely or with a shine. And you could also call something greasy, meaning that it looks like it's covered in a thin layer of grease. Streak is defined as the color of the powdered mineral. Now you might say, well, the color of the powdered mineral will match the color of the mineral specimen, right? You would be wrong. So take, for example, these 3 samples of hematite that look drastically different. But when we powder them, you will see that they're all the same. So to take the streak, what you do is you hold your streak plate and you drag your mineral across it. Now, hematite has a characteristic red-brown streak. And this will be the one that surprises you the most. Because you see that they are all the same color. Isn't that amazing? Some things are less exciting. If we take our sample of pyrite, we get this dark gray streak when we started out with a brass-colored mineral. And of course, some minerals that are one color will give you the same color streak. Make sure that you select the correct streak plate. We have white varieties and black varieties, and that will allow you to see the color more clearly. For example, if you streak white on white, you might not be able to see it very clearly. Now, a word of caution is necessary here because the sample must be weaker than the streak plate. We'll talk about hardness in a moment, but in order for the streak plate to create a powder, that sample must be softer than the streak plate. Measuring the hardness of a mineral, defined as the resistance to scratching, will be one of the most helpful and also one of the most difficult. We use the Mohs hardness scale, which was developed by German mineralogist Friedrich Mohs. He was born in 1773 and died in 1839. On this scale, you see that every whole number is characterized by a mineral. You also see that we have half numbers here. On the Mohs hardness scale, we don't get any more precise than a half step. So you might say that talc has a hardness of 1 and gypsum has a hardness of 2. There are some common objects that we can use to determine hardness. Your fingernail has a hardness value of 2.5. A copper penny, an old copper penny, not one of the new ones, has a hardness of about 3. And an iron nail has a hardness of about 4.5. So the nail will scratch the copper penny because it is harder than it, just like the copper penny will scratch your fingernail because it is harder than it. Talc is our first mineral on the Mohs hardness scale, and it is the softest. As you can see, it rubs off on your fingertips. Talc is what makes up talcum powder, by the way. Representing the value of 2 is gypsum. Gypsum is used to make wallboard, so if you enjoy living indoors and you have drywall, you can thank gypsum. Now, gypsum and talc are both less hard than your fingernail. So, to show you, here I have scratched this sample of gypsum, and you can wipe it off on your finger to be sure. The next specimen that we have is calcite, which has a value of 3. Now, because the copper penny and calcite are so similar, and honestly because the copper penny is so small, I rarely use it. But you could compare the iron nail to calcite, and you will see that I am able to scratch the calcite with the iron nail because the iron nail is harder than the calcite. Representing a value of 4 is fluorite. Fluorite is named because it fluoresces under UV light. Now, an important thing to note is that every mineral, as we progress, will scratch the one before it. So this fluorite sample we could use to scratch the calcite. And so you see that I have made some gouges in the calcite here. And there's powder on the tip of this fluorite, but it has not harmed the fluorite because, again, the fluorite is harder. Similarly, this nail will scratch the fluorite. However, the nail will not scratch the apatite because apatite is harder than our iron nail. So what happens in this case is that if there's any weakness on this, it will break it off. But you could potentially leave a streak of the nail on the surface of the mineral, which it appears I have done. I haven't left a gouge in the mineral. I have left a trail of the rust from the nail on the mineral. As we continue to become acquainted with materials of higher value on the Mohs hardness scale, you see that we can also use a glass plate. Now, you could be mean and use the window pane, but I would encourage you to use one of the glass plates that we provide for you in lab. Anything harder than 5.5 will scratch the glass. So this sample of apatite, which has a hardness of 5, will not scratch the glass. In fact, you see that the dust that I created is wiped off and there is no gouge left in the glass. Representing a value of 6 on the Mohs hardness scale is a mineral called orthoclase feldspar. Another name for this mineral is potassium feldspar, and you can shorten it by using the chemical symbol for potassium, which is K, and then just spar. So you'll hear me refer to this as K-spar. Another way to remember the orthoclase is that your gums are pink, similar to this mineral here, and you go to the orthodontist to get your teeth fixed. Now this K-spar, because it is harder than glass, will scratch the glass. So pay attention, because what I commonly see is people going like this. Oh, it doesn't scratch. You need to put a significant amount of effort into scratching this glass. So put all of your weight into it, hold the glass, it's sanded on the edges so it won't cut you, but put some effort into it and you will hear the scratch there, and you will feel the scratch with your hand when you wipe it off. So can you guys see that scratch there? It's there. If you're not sure if you've scratched the plate, you can also run your fingernail over it, and your fingernail should catch. And then you know that you have scratched the glass. Another common mineral that is harder than glass is our friend quartz. So quartz, again, will scratch the glass. And be careful to wipe it away, because you will see that you might have some little pieces that break off because of weakness in the mineral, but those were going to break off anyway. But nevertheless, you have scratched the glass. Representing a value of 8 on the Mohs hardness scale is topaz, which is the November birthstone. Again, this will easily scratch glass. And we also have corundum, which makes up rubies. This is an example of a prismatic crystal. You can see that it has 6 sides and is elongated. And you can also see that this crystal has some weird stuff on the outside. So when we measure the hardness of this, this might give us an erroneous value. So we want to try to measure the inside. So I'm going to measure up here. And again, we see that we have very easily scratched the glass. Now, for obvious reasons, I don't have a sample of a diamond. We do have some samples in the lab, but they are so small that I didn't even bother bringing it today because I knew that the camera would not pick it up. A word of caution about using these scratch plates. As you use them over and over and over again, you will find that they accumulate a lot of scratches on them. When this starts to happen, make sure that you go in a different direction when you test your mineral. And that way you can see when you have successfully scratched the plate. Another tool that you can use is unglazed porcelain. Unglazed porcelain has a hardness of 6.5. So anything harder than the unglazed porcelain will scratch the streak plate. And this is important because when you're determining streak, you cannot do that for these minerals because they are harder than the streak plate. If it is absolutely necessary to determine the streak of a mineral that is harder than the streak plate, you can use a hammer to powder it and then observe the color that way. But for the purposes of introductory geology, you don't have to worry about doing that. Remember, when we're talking about cleavage, we are talking about regular, repeating, parallel breakage surfaces. So if you think that you see a plane of cleavage, make sure that you see it over and over and over again. And the reason that this exists is because we have weakness in the crystalline lattice. So in this example here, let's imagine that all of these bonds in this direction are the weak ones. So everything will break here if pressure is exerted on this sample. So in this sample, we're going to break it, and then this will come apart because this is the weak bond direction. So this is the fundamental concept of cleavage, is that you have a weakness in the crystalline lattice that determines where it's going to break. Now, we don't know exactly what shape it's going to break into, but we do know the angles that it will break into, again, because of this weakness dictated by the crystalline lattice. One thing that we can talk about is perfect versus imperfect cleavage. Now, this is a sample of muscovite mica, and muscovite is known for having one direction of perfect cleavage. And in fact, you can even see through the sample. Now, it's very strong in one direction because it's covalently bonded, but where you can peel it apart like pages of a book, this has very weak bond directions separating these more strongly covalently bonded layers. So again, this is one direction of perfect cleavage. Because we only have one direction, we call this basal cleavage or book cleavage. And again, this is muscovite mica. I like to call this white fish food because it looks like flakes of fish food. Another thing that you can call it is nature's glitter. If we have two directions of cleavage, we call that prismatic cleavage. So we can have cleavage angles that intersect at exactly or about 90 degrees, or we can have cleavage angles that intersect at angles that are not anywhere close to 90 degrees. And a common one is 60 degrees and 120 degrees. Now, you might be thinking, okay, if we think about this in terms of length, width, and depth, and we have two directions of cleavage, then what is the other direction? So that other direction is a fracture. So let me show you. In this case, this is our specimen of plagioclase feldspar. And in this case, we can see that we have a break right here, and we can see that repeated here and here and here. And if we flip the sample around, we can see that this is repeated right here and right here. And this surface right here is a repetition, and this surface up here is a repetition. We can see a little step right here. So this is our first cleavage direction right here. The next thing that we can notice is that we have this very nice surface here and this very nice surface here. And if we look, we see that we have a couple little stair steps repeating up here. And this is all parallel to this same direction. So remember, when we're looking for cleavage, we're looking for regular, repeating, parallel breakage surfaces. And that's exactly what we see here in this sample of plagioclase feldspar, where we have two directions of cleavage at about 90 degrees to each other. So what about that third direction? We have one cleavage like this, one cleavage like this. So let's look on this side. On this side, we see that we have fracture. We do not have a nice clean break. We do not have a preferential breakage direction. So in this sample, we have two directions of cleavage at about 90 degrees to each other. Therefore, we would call this prismatic cleavage. Now notice when I was handling this sample, I did a lot of flipping it around. You need to look at different layers. You need to look at different areas. You need to hold it in different directions to see how that light reflects. Sometimes you're not looking at what is there. Instead, you're looking at what is missing. The human brain is absolutely spectacular at pulling out imperfections. So sometimes it's easier to find what isn't there. In this sample of selenite gypsum, we can see another example of prismatic cleavage, but in this case, it is not at 90 degrees. It's at about 60 and 120 degrees. So if we zoom in a little bit, we can very clearly see these sort of spiky stair steps that are up here. And this is your indicator that you have cleavage in this direction right here. And you can see in the interior of this transparent crystal that there are some lines that extend parallel to these breakage surfaces. Maybe a little bit better on this edge. These are not scratches. These are weaknesses in the crystalline structure where it has started to break but hasn't totally broken. So one direction of cleavage is like this, and the other direction of cleavage is like this, because you can see the tops of these stair steps here. Boom, 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 boom. And you can see that we have a pretty nice break up on this edge that is, again, parallel. So again, we call this prismatic cleavage because we have two directions of cleavage, one right here, one right here. So what about that third direction of cleavage? If we look here, we see that it is not cleavage at all. We see that it is a rough surface with no sort of preferential break. So again, this third direction is not cleavage, it is fracture. If we have three directions of cleavage that all intersect at right around 90 degrees, we call this cubic cleavage. Now, the shape of this sample looks like a cube. But again, this could be cut, so we want to look a little bit closer at the sample. And as I rotate this, you should see that there are squares or rectangles missing. So again, in this case, we're not necessarily looking at what's there, but it's what's missing. So especially right here, on this corner, we can see that there are cubes that are missing. So obviously, we have one cleavage direction in this direction, and we can see that repeated over and over again. One cleavage in this direction, and one cleavage straight up and down. So cubic cleavage is my example of a shoebox. If you purchase a new pair of shoes and you have a shoebox that came with it, then you're going to have a shoebox with nice 90-degree angles. So remember that just because it's called cubic cleavage, it doesn't mean that you will always have cubes. It just means that those angles will be at 90 degrees. Now my example of a smushed shoebox is rhombohedral cleavage, which you now see in the picture. Rhombohedral cleavage I like to call a smushed shoebox because this one has survived a couple moves perhaps. you have changed apartments a couple times, and in the process it's gotten a little bit beaten up. Now you still have a shoebox, it's just a little bit smushed. And this is because you have 3 directions of good cleavage, but they are not at 90 degrees to each other. So this sample of dolomite has cleavage at about 60 and 120 degrees. So very obviously, we have a length, we have a width, and we have a depth of cleavage. So here's another sample of, this is a sample of calcite, which is similar to dolomite. It also has rhombohedral cleavage. And you can very easily see that we have this rhombohedral cleavage. But you see that something weird is happening right here. And so cleavage can be very useful for determining how many single crystals you have. Because as these crystals were growing, the solution that it was formed from, the water that it was formed from, were adding another layer, another layer, another layer of atoms. But what happened here is that we had a separate crystal growing. And so it formed different cleavage surfaces that are parallel to only that crystal. So we can see this is one crystal right here. And we see that this is a second crystal right here because those cleavage surfaces do not line up. However, because it's all calcite, it all has the same type of cleavage. It all has rhombohedral cleavage. It's just in different directions. So we have rhombohedral cleavage right here. We have rhombohedral cleavage right here. We have 2 separate crystals in this one mineral specimen. The next 2 types of cleavage are very difficult to see because we don't have, well, our samples get broken by you, and that is absolutely wonderful. But the problem is that our samples don't stay solid for long. So this is a collection of specimens of the mineral fluorite. And you might see that they have some surfaces, but they don't necessarily look like they're intersecting at 3 directions of cleavage. Fluorite actually has 4 separate directions of cleavages. These 4 main cleavages intersect at about 71 and 109 degrees. And in a perfect world, this would form little octahedron-shaped specimens. But in reality, what we get is sort of fragments of these octahedra. And this can be challenging, so this is why you need to look at cleavage and hardness and streak and all of your other physical properties that we've covered today. There is one final type of cleavage, which is called dodecahedral cleavage, that we do not have any specimens of, so I cannot show you. But these have 6 cleavages which intersect at 60 and 120 degrees to create dodecahedrons. The only mineral that you might see this in is sphalerite, which is in mineral box 2. But again, the specimens that we have do not show this type of cleavage. When you're looking at cleavage, sometimes it will be very easy to see. For example, this is one very nice smooth surface here on this calcite. But on this side, it looks more like stair steps. And so it's worthwhile to discuss the difference between perfect and imperfect cleavage. On this side, it's one nice plane. On this side, it's a series of stair steps. And this is why it's so important to flip your sample around, look at all of the different angles in order to see, do you have perfect cleavage? Do you have imperfect cleavage? Sometimes it will be easier to find than others. To complete this discussion of mineral identification, I'm going to talk about a couple weird things. And the first thing is effervescence. Effervescence is what happens if you put hydrochloric acid on a carbonate mineral or any mineral that can have CO2 liberated from its crystalline structure. So in this case, we're using 5% diluted hydrochloric acid, or HCl, and you can say that it effervesced, or you can say that it fizzed. It doesn't matter to me, but Effervescence is a good way to tell what mineral you're looking at. For example, consider these two specimens. Here we have calcite, and here we have dolomite. They're very similar. They're close in hardness, although dolomite is a little bit harder. They both have rhombohedral cleavage, and sometimes they can be very similar in color. One of the major differences between this, other than the hardness, is that calcite will fizz with exposure to hydrochloric acid, whereas dolomite needs to be powdered first. So here I will put a drop of hydrochloric acid. And in case the camera isn't picking that up, you can hear it fizzing using the audio. It's very easy to see the fizz in person, I promise you that. To maintain a clean lab, let's make sure that we pick up the hydrochloric acid as we put it out. Now, if I were to put hydrochloric acid on this specimen, it would not fizz, and I'm not sure that the camera is picking it up, so I'm not going to bother. But it will fizz if powdered. So what we can do here is grind a little bit of the dolomite onto the streak plate, because remember, it is softer than the streak plate, and then you should be able to see it fizzing here. You can see the production of the bubbles. Sometimes it's very strong, sometimes it's a little bit weaker. This is right around in the middle, but you can see that this specimen has fizzed when powdered. Again, this is called effervescence. Another strange thing that I want to talk to you guys about is the presence of striations. These are our two types of feldspars that we're going to cover. Remember that we can also have a white variety of plagioclase feldspar, or we can have this darker variety here. This is plagioclase feldspar. This is potassium feldspar. They're very similar. Their cleavage directions are right around 90 degrees. Their hardness is right about the same. The difference is their color. But you can also look on plagioclase feldspar and see little lines along the cleavage surface. So this is what the camera is picking up right now. You can see these little lines, they're called striations. And they will only form along the cleavage surface. So if you're holding a specimen of plagioclase feldspar and you see these lines, then you know you've got cleavage, you've got plagioclase feldspar. On the other hand, you can see that there's a similar striped appearance for this sample of potassium feldspar, and you can see these lines here. These are called exsolution lamellae, and they form because a small amount of plagioclase feldspar, this guy, grows inside this crystal as it is growing. So if you see this striped appearance in a pink rock, you know that those are exsolution lamellae, and you are looking at orthoclase or potassium feldspar, or a shorter version of that is just K-spar. Some minerals, as I have already pointed out, are magnetic. So this is a sample of magnetite. Occasionally, other minerals will be magnetic. Hematite can sometimes be magnetic, for example. And finally, I would like to offer you a word of caution about how you collect your measurements. In each of these specimens, there are inclusions of other materials. So if you are testing your mineral, you want to make sure that you are taking your readings from what is representative of the mineral. For example, in this specimen of plagioclase feldspar, you see that you have a small inclusion of quartz. So if you do your tests on this quartz, then you will successfully identify quartz, perhaps not potassium, or perhaps not plagioclase feldspar. The same is true for this sample of galena, where you see that we have an inclusion of a white mineral that has grown next to it. When you're doing your hardness, do not test this white mineral. Test the side that does not have any indication of having an inclusion. Finally, you see in this sample of hematite, we have these white inclusions in it. Make sure that you're testing along another side, not where that inclusion is, in order to correctly identify this mineral. And to end our review of mineral identification, I will leave you with a little joke. This is our specimen of galena, and remember that it has cubic cleavage. So if we were to break this, it would snap into many, many small cubes or rectangles. So the joke is, if a house falls down in Galena Park, what shape does it break into? And the answer, of course, is little fragments with 90-degree angles, because obviously all of the houses and buildings in Galena Park will have cubic cleavage, just like galena.